Okay, welcome everyone. So I'm going to talk today about the prediction of NMR parameters, particularly focused on solid state NMR. I'm going to give a number of different examples to a whole range of materials, ranging from sort of organic pharmaceuticals through to sort of inorganic materials. But I'm going to give a little bit of scene setting first, and a little bit about what is NMR and what can we do with this. So I guess the conceit in sort of computational material science is that we need to know the atomic structure of materials. If we're going to think about designing new materials, we need to know what the atoms are doing in our existing materials. And you know, the preeminent tool to really examine crystal structure is X-ray diffraction. But of course, that doesn't often give us the whole story. Perhaps we've got some disorder in there. Perhaps our crystallites are particularly small. So we may need additional information in order to figure out what's going on inside our materials. Perhaps there's dynamics involved as well. Okay. So the idea of computational spectroscopy is that we can take some knowledge of what the material is and use first principle simulations, so simulations that are built on quantum mechanics, to try to predict experimental observables. So that could be what we would see in an NMR experiment. It could be things like vibrational spectroscopy, IR, Raman. It could be electronic spectroscopies, things like X-ray or EELs that we might see in an electron microscope. So I'm going to focus, CASTEP as a software program is able to predict all of these different types of spectra from a common crystal structure, so it's rather powerful. But I'm going to focus this morning on NMR. So the idea of NMR is that we want to use the atomic nuclei as spies. We want them to report back on their local environment. Okay, and specifically, what we're going to measure in an experiment is their resonant frequency. So the idea that certain nuclei, say a spin-half nucleus like carbon-13 or a proton, is spin a half, and so in a magnetic field its energy levels split, and NMR allows us to very accurately measure that resonant frequency. Okay, now the challenge with NMR is that whereas in diffraction we have Bragg's law, and Bragg's law helps us interpret what we see in terms of experiment and relates it back to the crystal structure, there's no easy theory that allows us to interpret what we see in an NMR experiment. What we see in an NMR experiment is related to how the electrons behave in a magnetic field, and that fundamentally comes down to quantum mechanics. Okay. So what we're going to provide in terms of a DFT code like CASTEP is a means of decoding what is going on inside our NMR experiment. How do those frequencies that we see relate to the underlying chemical atomistic structure? Okay, so again, just a little bit of overview of NMR. So if we think of a simple spin a half nucleus, we apply our external B field, we give a tendency for the spins to align with the field. Bit of the back of the envelope calculations instantly tells us that NMR is a relatively insensitive technique. So it's typical fields, 10 Tesla, that we might have in a typical lab spectrometer, and at room temperature, the populations aligned with and against the field are almost equal to each other. Okay, so it's a very small population imbalance that we're trying to measure. So you're not going to be measuring NMR from a single atom, you're going to be measuring it for an ensemble across the crystal, and that's important to keep in mind when we interpret what we see in the calculations. Okay, so what sort of nuclei can we look at? Well, obviously hydrogen, so what would be essentially a proton is a good one. It's almost all of the protons are spin a half, and so they're easily observable. Carbon-13, quite common, but of course note the abundance here is rather low, so either one has to wait a bit longer, or one might think about selectively doping. Some good material science elements, so silicon and phosphorus, both spin a half, and both relatively amenable to NMR experiments. What about some more interesting nuclei? So oxygen and titanium. a couple of challenges here. So something like oxygen is only present in 4 parts in 10,000. So to do oxygen NMR, you're going to need to enrich. And in both cases, these are not spin a half, these are quadrupolar nuclei. And we'll find that to be the case for many of the transition elements that, things further down the periodic table. They won't be simple spin a half, there'll be higher spins. That does have an implication for what we calculate. There's some extra parameters that CASTEP is able to calculate to interpret these quadrupolar nuclei. Okay. And really, this has been the development for experimental solid-state NMR over the past 20 years, has been the ability now to have higher magnetic fields, more complicated pulse sequences, and to be able to do these more interesting but challenging nuclei such as oxygen and titanium. NMR really is a multi-nuclear technique, able to look at all the elements in the periodic table, and we aim to make sure that the calculations can match this. Just very simply, in case people aren't familiar with the technique, here are a couple of NMR spectrometers in one of my collaborators' labs up in St Andrews. Okay, most of what you're seeing there is actually the cooling for the superconducting magnets. Okay, so just a note on solution versus solid state. So a lot of the NMR that is done is solution state. So there you've got a liquid, the molecules in there will be rapidly tumbling, and that gives you very sharp line shapes. The situation is different if you look at what solid state NMR, typically you'd be looking at a powdered solid, and what you have there is lots of crystallites orientated sort of on sort of a random way. And so instead of seeing an average, you would see a superposition. So if you didn't do anything special, you would get a very broad featureless signal. And the challenge experimentally in solid state NMR is to do what's called magic angle spinning, to spin the sample, to reintroduce some time dependence into the problem. And with that, you can start to recover these sharp line shapes at the average value of the appropriate tensors. The solid state NMR also gives you the power to start to look at the full tensors available. And with DFT and CASTEP, we're able to predict the full tensors, not just the isotropic values. Okay. So a number of years ago now, in collaboration with Chris Pickard and Francesco Mauri, we developed a set of computational approaches in order to predict NMR parameters truly in the solid state. Okay, and CASTEP was at the forefront of this because with Chris and I as developers of the code, it was natural for us to implement these theories first within the CASTEP code. So this is using density functional theory, it's using a plane wave basis set, and it's using periodic boundary conditions. So essentially the input parameters that you would need would be the unit cell, ABC, alpha, beta, gamma, and at least a reasonable guess at the atomic coordinates. Okay, so we're studying the crystallographic unit cell. You could, if you wanted to study, for example, an isolated molecule, perhaps you're trying to compare against solution state NMR, you could do that by studying a molecule surrounded by vacuum and then the periodic boundary conditions. So an array of isolated molecules, and that's possible to do. Okay. So the key NMR parameter, perhaps the most useful NMR parameter, is the magnetic shielding. And this comes into play because we're measuring the precession frequency of the nucleus, and that is related not to the applied magnetic field, but to the magnetic field actually at the nucleus. Okay, so that changes very subtly depending on the chemical environment, and that's due to the magnetic shielding effect. So what is happening is his big aromatic molecule, imagine the magnetic field is out of the plane towards you, and you have a current, an electronic current that's induced by the magnetic field that circulates around. This is diamagnetism. Okay, and that current will create a magnetic field that varies at different points in the crystal. So different nuclei experience different magnetic fields and resonate at a slightly different frequency. And so what CASTEP does is it computes the current. Okay, it computes this induced current, and hence using what was essentially the Biot-Savart law, it can compute the magnetic field of the nuclei. Okay, so what we get is something like this. Here is a typical solid state NMR spectrum. It's on a fluoroprofen pharmaceutical compound, and it's carbon-13, and each carbon atom has in a different environment resonates at a slightly different frequency, giving rise to a slightly different peak. But what CASTEP is able to do is tell you which peak is which. Of course, quantum chemistry methods have existed since the 1960s in order to be able to predict NMR parameters in isolated molecules. They came online really in the late 90s. Just this point of this slide is to say, if we do an isolated molecule, we will be able to get the same answer that you can get with a code such as Gaussian. Okay, so this is a comparison of the GIPOR, which is CASTEP, versus a quantum chemistry code for a range of different atoms, and you can see in some different isolated molecules, and you get extremely good agreement. So if we want to be able to do molecules, we can do. Key difference with CASTEP here is that we're going to be able to calculate things truly in the solid state. Okay. Why is that so particularly important? So here's an example. This is a two-dimensional NMR spectra recorded on maltose, which is a sugar disaccharide used in brewing. And this is a 2D correlation spectra. So the cross peaks here. So on the skyline here, you get the carbon frequencies, and on the vertical, you get the hydrogen frequencies, the proton frequencies. And the cross peak happens when you have carbons bonded essentially to protons. So this is picking out all the CH pairs in the sample. So let me first of all do a CASTEP calculation in which I treat the system as an isolated molecule. Okay, I get the blue crosses, and they're not disastrous. They're on the right graph. They sort of seem a bit shifted, but if I move this one down here, I'd have to move this second one a huge way down to match over. So I can't trivially just move that around. So that's not disastrous, but not great. I've treated it as an isolated molecule, but it's not. In the spectrometer, it's a solid. It's a 3D molecular crystal. So let's do the calculation with CASTEP on the 3D molecular crystal. And now we get the red crosses, and you see much, much better agreement. And that enables us to make an actual assignment of the spectrum. Okay. This is another pharmaceutical. So this is a more complicated solid. And we're making a pretty good assignment of all of the peaks. Occasionally we will get some systematic errors. If you look at the spectrum here around 130, you see there are two peaks, but they're slightly shifted over. Okay, that probably doesn't preclude you from actually making the assignment there. Okay, so that's a reasonably good assignment. Here's an example that we did with AstraZeneca, published a couple of years ago. And here they were concerned because if you look at this particular pharmaceutical compound, this is its chemistry structural database name, BIYSEH03. For this particular compound, there were a number of deposited structures in the database, and some of them had rather poor R factors. Okay, the question is, which should you trust? So one of the things that we were able to do here is take these two structures and then do some geometry optimizations on these two structures, and you can see there was some movements, for example, in the second ring. And then we were able to, obviously there's only one true structure, and that's the one we were able to do the solid state NMR experiments on. And one of the things is, once you do the full geometry optimization, these two structures essentially become equivalent. Okay, so they both give reasonably rather good actually agreements for both the carbon-13 and the proton spectra, enable you to make a reasonable assignment of the peaks. But essentially what we're showing here is that we can improve the confidence in some of these structural models that come out by doing both the full this geometry optimization, and then by doing the geometry optimization to confirm that yes, this is a good structure for this material. Okay, so that was published in say Crystal Growth and Design with the team from AstraZeneca and a number of other partners. AstraZeneca, working with AstraZeneca, we came up with a protocol for how they, for example, run CASTEP NMR calculations, the settings they use, why they've chosen them, and that's a public protocol, so you can download that from the CCPNC's website. This is a UK institution, and more on that a little bit later. Okay, so that's a little bit on organic materials. Just if I change gears, this was a study with a group in Orléans, where we were trying to examine disorder in some double-layered hydroxides. So we were looking at both typically hydrogen NMR spectra in these layered materials, and trying to quantify. This is the brown thin line here is the fairly broad pattern that you'd see in NMR. And there are a number of different underlying peaks that are available under here, and we were able to then say, using the calculations, we were able to determine which type of defect environment would contribute to which type of hydrogen, and so quantify the nature of the defects in the real materials. So that's looking at materials that are disordered. Here's some truly amorphous materials. This is germanium selenium glasses, and you can see in the top the black traces are a variety of glassy compounds with different stoichiometries. And there are obviously peaks that are appearing here, and the question is, what do these correspond to? That was an open question before we got involved. And what we had here was a set of snapshots from molecular dynamics, and they captured a range of different, this is doing selenium-77 NMR. We have done some germanium NMR, but that's not shown here. And so in these glassy models, you can identify a variety of different selenium environments, from edge sharing to corner sharing to isolated selenium atoms to seleniums connected to two other seleniums connected to a germanium, etc. And by calculating the NMR properties and correlating them with what type of selenium atom they are, we could provide what the ranges are. So the peak over this side is always a selenium connected to two other seleniums. The corner sharing can have quite a range of different chemical shift environments, and so we were able to then start to give an atomistic interpretation of what these solid-state NMR experiments on the amorphous materials mean in terms of the underlying chemical structure. Okay. Here's a study from Andrew Morris's group, who is in Birmingham in the UK. And Andrew's very focused on looking at materials for batteries, both anodes, cathodes, and the solid electrolytes. This is a study looking at the lithiation of phosphorus. I think he also added in a separate, in the same study, he also looked at adding sodium in. And you can see, so what he has done, this is actually, he's used the Ayres random structure approach to predict the structure of lithium phosphates with different lithium contents, and then taken those low energy structures and predicted their NMR spectra. Okay, so as we increase up the graph, we're increasing the amount of lithium content. And you can see the general trend, which is that the chemical shift moves to more negative values. Okay, so this starts to give you then a kind of fingerprint, a way of interpreting what you might see as you, for example, did discharge experiments on these phosphorus anodes. So those examples all focus on the chemical shift, the magnetic shielding effect, and that is most common and the sort of dominant effect in many cases. But CASTEP can look at the full range of NMR parameters. So just to summarize those, the quadrupolar coupling is essential if you're going to look at any material that's quadrupolar. Okay, so quadrupolar nuclei, to interpret their NMR spectra, you're going to need the quadrupolar coupling as well as the chemical shifts, and more on that in a moment. The kind of lowest frequency interaction would be the J coupling, the spin-spin coupling between two nuclear spins, and again, that's something that CASTEP can calculate. So a little bit more on these properties. So the electric field gradient is actually just a function of the ground state charge density. So slightly more, it's much easier property to calculate in many ways, and actually a number of different codes are able to calculate the electric field gradients. Okay, so NMR shielding calculations are a little bit time consuming. They often take maybe 5 or 6 times what a ground state calculation would take, but the electric field gradient is essentially a post-processing step after the ground state calculation, so it's relatively quick. Okay. The electric field gradient gives you both the quadrupolar coupling and the asymmetry parameter. Quadrupolar coupling determines the width of the line shape, and the asymmetry gives you the particular line shape that we have. So this is an example looking at an amino acid whereby there are 4 different oxygen atoms. 2 of them are OHs, 2 of them are carbonyl oxygens. They do nicely split into 2 sections, but there are some strongly overlapping peaks, and it was only with the calculations that we could assign one particular peak to a particular atom. Okay, just a note here. So with the chemical shielding, we did the validation on molecules, isolated molecules, against a quantum chemistry code such as Gaussian. How could we sort of validate our accuracy for the electric field gradients? Well, this top graph on the right-hand side shows the comparison of the plane wave pseudopotential with our Paul reconstructions, that's with CASTEP, against the kind of benchmark code, if you like, the all-electron code V2K, and what you get is really very good agreement between the all-electron V2K and the pseudopotential approach within CASTEP. Okay, so we really are able to get all-electron accuracy for these properties. The lower figure here is actually the comparison against experiment for this particular range of systems. What's interesting, of course, is that the agreement between the codes is very much better than the agreement with experiment, which is still itself very good, but it means that any discrepancy between codes is very small in comparison to the discrepancy you'd see with respect to experiment, and that's good from the computational accuracy point of view. One of the interesting things with the electric field gradient is it's not limited just to diamagnetic insulators. So you can calculate electric field gradients for all particular scenarios, in the sense that you can do calculate it in metals, and you can calculate it in paramagnetic compounds. So this is these are sodium NMR. It's a layered vanadium phosphate compound. The sodiums, the pale blue atoms, sit in the interlayer regions. And this is paramagnetic. Okay, so it has unpaired electronic spins, but we can calculate the electric field gradients here without any problems. There are 2 sodium sites here, and the calculations do a good job at predicting both the CQ and the eta Q, the asymmetry. The agreement is somewhat better for these for the first sodium site compared to the second sodium site, but it's still possible here to assign each of the 2 sites. So that's an example of looking at paramagnetic material. Okay, so then on to the final the third NMR parameter, which is the so-called spin-spin coupling. So this is the interaction between 2 nuclear spins. So I've got two nuclear spins, and There's an energy difference between having those spins aligned and having them anti-aligned. Okay, and there's two components to that. One of them is a through space interaction, so it's a simple dipolar interaction. That doesn't involve the electrons, it doesn't involve any quantum mechanics, and it can be predicted simply from the crystal structure. But the J coupling is instead, it's the electron mediated interaction. So we have a magnetic spin on the first nucleus, and it polarizes, well, it interacts with the electrons, and those electrons interact with another nucleus, and that creates the interaction. And it can do that via two ways. It can do it via the orbital motion of the electrons. So the red atom creates a magnetic field. The electrons see the magnetic field, that causes them to start circulating, and the blue atom sees the circulating electronic current and experiences a magnetic field, and hence the interaction between the red and the blue. The other approach, the other mechanism by which the J coupling is mediated is that the nuclear moment, magnetic moment of the red atom creates a spin density, which then this polarization propagates across the bond and induces a spin density at the neighboring atoms, which feel a magnetic field via sort of hyperfine and dipolar terms. So CASTEP is able to compute the J coupling from both of these two parameters. How well does that work? So these are a range of phosphates. I've got some lead phosphates and some calcium phosphates, pyrophosphates. I haven't got the experimental error bars on this, but they are the order of a few hertz. But we're doing quite a good job here at predicting how the J coupling between these are phosphorus two bond J couplings, how these are the experimental measurements and the calculations are actually in really good agreement over quite a wide range of couplings. These are not easy experiments to do, I should add. Some examples on some molecular crystals. So this is uracil. It's a planar compound, and so we were able to make a couple of predictions here, confirmed by experiment. So we can calculate the J couplings between these two nitrogen atoms, and also J couplings across the hydrogen bond between the oxygen and the nitrogen. Okay. There are two different hydrogen bonds here, giving rise to slightly different J couplings, and pleasingly the calculations do a very good job at reproducing what we see in experiment. We did something similar for guanosine, looking at nitrogen-nitrogen, where again there are different types of hydrogen bonds. Something important I should add here, which is that this was the first example of oxygen-nitrogen J couplings measured in a solid. And actually, we did the calculations first. Okay, these were not easy experiments to do. They required some enrichment, and so we did the calculations first. And then, when we proved that they were big enough to be measurable, the experiments were then done. And we work that way quite often, although it's not apparent from the published papers. That often people will do the calculations first to see if it's worth doing experiments, to see what you would learn. You know, can you see some significant differences? Are the differences going to be big enough to be experimentally significant? And then once you've done the calculations first, only then do you go and do the experiments. So that's for us is a relatively common way of working. Okay. This has also led us to look at some more unusual interactions in NMR. So number of years ago, a collaborator, Sharon Ashbrook in St Andrews, brought me this particular set of experimental spectra where it appeared that she was seeing J couplings between fluorine atoms. Okay, and then, for example, we expect to see between, and this is a deep earth mineral, clinohumite, and she was seeing J couplings between the pale blue atoms here and here, F1 and F3, while they were relatively close and only 2 bonds apart. But she was also seeing what looked like a J coupling between F1 and F7. So in a chemistry sense, these atoms are not bonded at all. They're quite distant from each other, and you'd have to go via a large number of other bonds in order to get from one atom to another. But we were able to see these couplings in experiment, in the calculations. So the calculations also reproduced these rather small J couplings. So that confirmed this was real. These were not artifacts of experiments. This was something we were actually seeing. And what these are is through space J couplings. So this is something that's now reasonably widely studied. There have been many more examples found in the literature. But we shouldn't think of J couplings as something that's always transmitted via a bond. So the calculations give support for seeing more unusual effects within the experiments. Okay. I just want to take a pause. So all of the calculations that I've shown you have been done typically with a simple GGA functional. So we like to use the PBE functional, and instead everything you've seen so far has all been calculated with PBE. And if I was giving this talk 4 years ago, I would have said that was the functional to use. You should definitely always just use PBE. We like these functionals as physicists because they're obtained from good sound, looking at the fundamental physics that density functionals should obey. So we've got this idea of this sort of ladder of functionals that we've got the simple LDA that depends only on the charge, and GGA, which depends on the charge and the gradient of the charge. And for those familiar with calculations, you'll know that LDA typically overbinds simple solids, and PPE will underbind simple solids. And if you apply them to a molecular crystal, it will be really bad, okay? There'll be massive changes in, for example, the lattice parameter, okay? Well, PBE is exceptionally good for predicting chemical shifts for most elements. There is a notable problem with PBE, which was fluorine. So again, a paper from a number of years ago looking at a range of fluorine-containing compounds, and we get very good, what seems to be very good agreement between calculation and experiment, okay, from a range of inorganic fluorides. You can include some organic fluorine crystals here. They all lie on a line. The problem is they don't lie on the right line, okay? The line they should be lying on should be parallel to this line here. So we would expect this to have a gradient of -1. So we're comparing the chemical shift delta, which is measured in an experiment, with the magnetic shielding, and they should have a relationship, a gradient of -1 between them, and it's not, okay? The gradient comes out something like about 1.5. Okay, it's very different. So that's always been a bit of a puzzle. So recently within CASTEP, we've been able to take the next step on this ladder, and so going beyond the GGAs to the meta-GGAs. And Perdue and Sun came up with the so-called scan functional that obeys all the known constraints. So this now, as well as having the charge and the gradient of the charge, also has the kinetic density involved. And it's been shown that scan is exceptionally good for lattice parameters. It's somewhere in between LDA and PBE, so not surprisingly, that agrees with experiment rather better. The blue down here is really very good. It also does quite good well at molecular crystals. So actually, here are some averages over some sets. This is an average bond length over a set of strongly bonded crystals. Again, scan is doing the best of the functionals here. And this is a set of molecular crystals. You see on average, LDA and PBE are very poor. We know that they don't have dispersion interactions. We include some dispersion interactions, we get them much better. Scan actually does a good job at including short range dispersion. Okay, so it gets molecular crystals by itself rather well. Unfortunately, the problem with scan is it was numerically unstable. It wasn't possible to construct pseudopotentials. It was incredibly difficult to converge results. So working with Albert Bartok, we came up with the R-scan functional, and this is the version that's within CASTEP, and it's also the version that obtained the results that I showed on the previous few slides. And scan and R-scan give you essentially the same bond lengths and lattice parameters. Okay. But the rate of convergence, the smoothness, is very much better with R-scan. Right, so what does that mean for NMR parameters? Should you be thinking about using R-scan? And I think you might. So just to say, in comparison, so delta is what you're going to measure in an experiment. Sigma is what you measure in the calculations, the shielding, and they're related to each other by this trivial straight line relationship. Okay, so there's the reference shielding, and there's a gradient of -1. So this is looking at some amino acids, and for carbon and oxygen, actually the RMS error from PBE and RScan is very similar. As I said, PBE does a good job at most simple structures, and so actually RScan doesn't necessarily improve very much. What it does do, though, is rather intriguing, is that it improves the experimental the reference shielding somewhat better. So the reference shieldings that you might use could be quite different between PBE and RScan. And interestingly, there are some experimental, it's quite exotic experiments, but there are some experimental reference shieldings around, and RScan is doing a much better job at predicting those. Now, in terms of interpreting your experiments, you don't care about the reference shielding. It's just a constant. It's just to enable you to make a comparison between the two things. So this by itself it's pleasing to me, but it's perhaps of no experimental importance. But it is nice that we put more physics into a functional and it does a better job. What about fluorine? Okay, so if we go back, so that we had the red line here, which was the PBE results with a gradient at about 1.4, 1.5. The RScan results are much closer to 1. Okay, so RScan, bringing in that extra piece of physics, is now doing a much better job at predicting the fluorine chemical shifts. So it looks like that's a problem that's essentially solved now. So I'd encourage you to explore the effect of the RScan functional in NMR calculations. Okay. Just to note that CASTEP can naturally include some relativistic effects. So because we use pseudopotentials, we can calculate those Corot electrons with a relativistic equation, some derivative of the Dirac equation. That can be important. So this is, for example, this is a complex involving phosphorus and silver. Silver is rather heavy. If you do a simple Schrodinger-like solution for the J couplings, you do a rather poor, it's not bad, but it's not a great description of experiment. If you include the relativistic effects within CASTEP, actually you do rather better. Okay, so CASTEP is, and the really nice thing about a pseudopotential code is there is no cost in including these scalar relativistic effects, okay, because of the use of pseudopotentials. Okay. Just some note about typical sizes. I mean, how big a crystal can you do? It kind of depends on how big a computer you've got, but it's a function of the number of atoms, but more strictly, it's a function of the number of valence electrons that's being used. Okay, so for a sort of pharmaceutical-based compound, something that's a carbon, hydrogen, oxygen, nitrogen in, a calculation on something with 1,000 atoms should be available on a modest size compute cluster these days. If you want to do 1,000 atoms of an inorganic compound, that will be pretty challenging. You can do that with the larger supercomputers. Typically, on an inorganic compound, 400 atoms would be a sort of sweet spot in terms of what you could do on a modest computer resource. The limiting step, as I said, an NMR calculation takes roughly 6 times the length of an SCF calculation. The limiting step is typically getting a good geometry, because NMR is super sensitive to the geometry, where all the atoms are. That's why NMR is a good technique, but it does mean that you need to know where the atoms are very precisely. So you need to do a good geometry optimization first, and that will typically be the slowest step in your computational workflow. Okay. Just to note that the number of input parameters for something like an NMR, a chemical shielding calculations, are really very low. Now, you may well be running these through Materials Studio, but just to highlight what's under the hood, CASTEP would take 2 different input files, a cell and a param file, and this would be a minimum input file in order to run an NMR calculation. It would be the lattice, it would be the positions of the atoms, it would be the sampling of the Brillouin zone, and you would tell it the functional, the cutoff energy you wanted to use for the basis set, and the fact that you wanted to do an NMR calculation. And that would be a sufficient input deck in order to do a good calculation. You would need, in order to do a good calculation, you're going to need to converge it. You're going to need to make sure you've got you've used a good enough basis set. You're going to need to make sure you've converged your k-point spacings. But those are the two parameters that you need to worry about in terms of getting a good, accurate calculation. Material Studio, of course, can set very good defaults for you, but essentially those are the two free parameters, and that's it. So that's actually fairly ab initio in terms of saying, give me an answer back. There aren't many options and keywords to play with at all, really, with the NMR calculations. Okay. Okay. So just to summarize, so what I've talked to you about is the so-called GIPOR approach, which is the theory that we use to predict solid-state NMR parameters within CASTEP. It's using DFT, plane wave basis, periodic boundary conditions. If you have a diamagnetic solid, okay, and that's most of the times what you're going to be doing in an NMR experiments on, we can calculate the chemical shift or magnetic shielding, the electric field gradient, and the indirect coupling, the J coupling. Okay. If you've got a paramagnetic solid, this is somewhat harder. This is still somewhat of an open question as to how do you properly predict NMR parameters in paramagnetic solids. There isn't a sort of one approach fits all, but CASTEP can look at some of the relevant interactions, so the hyperfine tensor and the so-called G tensor. The electric field gradient, of course, can be calculated both for solids, for diamagnets, paramagnets, and even metals. And we are continuing to work to improve the range of parameters available. So there's work going on in my group now to look at spin orbit effects. That has some profound implications for heavy element NMR, particularly light elements bonded to heavy elements. So that's something that we hope will be available in the future. And if you are interested in finding out more, there are two comprehensive reviews, one from Thibaut Charpentier from 2011, and one from Christian Bonhomme that I was involved in, which is in Chemical Reviews from 2012. And that was, at the time, they were fairly complete surveys of all of the applications that had been done. So I'll just end with some acknowledgements. Obviously, this is all work done within CASTEP, and I'm grateful to the CASTEP developers for their support. Within the UK, we have something called the Collaborative Computational Project for NMR Crystallography. I mentioned, for example, the protocol that we developed with AstraZeneca. There are other tools available to help visualization or support of interfacing between, for example, CASTEP and spin dynamics codes. And you can find out more about this on CCPNC's website, which I've given here. And I should just acknowledge the various people who have funded me over the years. And thank you for your attention.